about the matrix building in SOFA. Please go ahead.
Hello everyone. Today I want to present a topic about matrix building, as well as a second topic of LDL solver acceleration, which will for the matrix building. We'll see it later. And my name is Zeng. I'm a first year PhD student at laboratory iCube in Strasbourg, and I'm also a member of the team Mimesis, and as it's already a bit late, so I will accelerate also my presentation. Here I want to start from the dynamic equation, which we usually use for deformable object simulation in SOFA. And here, after linearization, we'll have a equation ax equals b, and that's a familiar equation. And in SOFA, to solve this system ax equals b, usually a common way to solve this system will be conjugate gradient algorithm. And in SOFA, for now, the fastest way of CG version will be a method without building the matrix, which means we'll never construct the matrix A, and we'll never store the A in the computer memory. But whenever we want to use the system matrix A and the vector B, we'll call a function at default which is defined in the tetrahedron FEM force field, and they will collect the necessary data, and they will finally serve for solving the system. And this function is already optimized in SOFA, and it can be very fast. And the following figure will show you a test result of runtime. The red line will be the CG of the version CPU, and the blue line will be the version GPU. We can see they can be very fast, and they increase with the iteration numbers. And we put also another line, which is the green line here. That is the result. It's the test result we have with the CG running on GPU, but with a matrix assembly. It will not start from zero, because we'll take times to assemble the matrix, and we can see that the matrix assembly can be quite expensive. So up to now, it seems to be totally worthless to build a matrix in SOFA, because the unbuilt method will be faster. But still, I want to explain some reason to build the matrix. And we come back to the CG solver. Whenever we want to solve the system, we need to call the function in tetrahedron force field. This function can be very fast, again, very fast. And but it is only defined in the tetrahedron force field, and it works only for the co-rotational model. And imagine a case when we want to use a new model or a new force field. We will take large efforts to parallelize the CG solver, and to avoid this case, once we have a matrix, we can put everything on GPU, and we can also benefit from the matrix built on sofa. In sofa, we can have easily have a asynchronized LDF preconditioner where we in our simulation we use the LDL factorization to construct a preconditioner, and we can also use the built matrix to it can be used in solving the contact problem. But as we can see in the precedent figure, the matrix assembly can be very expensive, and so I will introduce our new methods to assemble the matrix. Sorry, here is the step of matrix assembly. There are three main steps. The first step will be just collect the data. This step will be done by a function, very simple, very stupid, but very fast, and it's already optimized on CPU. And the second step will be the sort, because the first after the first step we have an unsorted and uncompressed format, and the sort stage can be quite expensive. It's the most expensive step during this process. And finally, with uncompressed formats, we have a compressed stage to finally have our matrix A and the vector B. Our acceleration will mainly rely on a case where our topology does not change. Imagine that if our topology does not change, the sort stage will always keep the same, which means we can simply skip this step. And in this case, we left the two steps: the add and the compress. The add is already optimized, and it can be very fast. And the compress stage, we can parallelize it on GPU. And here I will show the results of our assembly matrix assembly stage. We have a standard matrix assembly stage, which will take about 22 milliseconds. Which was presented in the figure, was the green line, and we have with our new method to assemble the matrix, we have finally time 3.3 millisecond on GPU. So that was a nice acceleration about the matrix assembly. So I want to come back to the figure of comparison, and I have added the latest version of matrix assembly. It is the matrix assembly stage will be quite fast, and despite we will take some time to assemble the matrix, we will have great advantages, such as we can already be compatible with the new models, with the new force fields, and more importantly, once we have the matrix built, we can put all the conjugate gradient algorithm on GPU, 100%. But that's for CG standalone. For if we have a preconditioned CG, we have another case where it remains a problem to solve. That is the application of preconditioner. here I want to show you a figure about how our simulation works. We'll use a synchronized thread to do the LDL factorization stage. It will transfer the transform A into LDL matrix, and this stage will be in the synchronized thread, but the LDL solving stage will remain in the simulations loops. And we can see here if we want to apply a preconditioner in CG, we need to solve the LDL matrix, and that happens also in the contactor problem when we want to construct the lattice operator. But why I say that it is a problem to for the LDL solving stage, because we have a primitive result. We have a LDL solver on CPU which can be very fast, and we have a standard version of the CPU which can be very fast, and we have a standard version of GPU where we use the CU-sparse library, which can be quite slow, and we also have a primitive GPU solver made by us, but it has an acceleration compared to the CU-sparse, but it's always takes more time than the version CPU. So in this case, to make the simulation faster, when my PhD work started, the LDL solver remains always on CPU because it's the fastest. And to accelerate the LDL solver, here we introduce a technique, graph partition, which will divide the matrix pattern into subdomains, and this allows us to solve the system with to solve the triangular systems with domain decomposition methods. And we have defined we have finally made our QDA kernel to solve the LDL solver problem. And I want to show you directly show you the LDL solver new version of the LDL solver on GPU. It's the final one, which we compared to our primitive version, which have a great acceleration, and even it's more faster than the version CPU. And so now we can see that we can put all the CG on GPU. So there will a great advantage will be that there will be no more data transfer between the two processors, between the CPU and the GPU, and which can be very expensive when the matrix is quite large. So that's our result of new LDL solver on GPU. And finally, I want to put some result here. Is the fastest implementation so far, which we have shown in the figure. Here we have the first one with limitation of iteration numbers with 25, and the second one with 100 iterations. They are fast, but they are not converged we have limited the iteration number, and the simulation works, but it lost some precision, and we have the final result. It is with our matrix assembly, and it with our latest LDL solver on GPU. And we can see that the CG solving stage can be very fast, and still we have to pay some time to assemble the matrix, but the final result is relatively fast, and it's precise. It's precise the simulation. So I want to have some little conclusions. For the matrix assembly, we have now assembly stage which will take only 3.3 milliseconds with with 8,000 loads, and now with the matrix build, we are already independent. During the CG solving stage, we are already independent of tetrahedron FEM force field in SOFA, and that means we will be compatible with new models. And we have now with the latest LDL solver, we are now we have now preconditioned CG algorithm fully running on GPU. We will no more have data transfer between CPU, greater data transfer between CPU and GPU. And finally, our LDL solver acceleration technique can be potentially applied in the contact program, which are on progress for now. And that's my presentation. Thanks for your attention. And
Thank you, ZQ. So that's typically the kind of of work and presentations, obviously, but work that would impact the work of everyone basically. If ZQ and with Adrian's team are actually accelerating, for instance, LDL, so direct solvers, even maybe to a point it can really compete with iterative processes. Means we could all finally not have those kind of iterative and approximated solutions at each of the time step of the simulation, but really get accurate simulation at each time step. So it's really a transversal work that could impact absolutely everyone. Is there any question?